Up next, Mark.
Hi, this is FiddlerBot. We've had him here before. Is that loud enough, or do I need the mic?
FiddlerBot, woohoo!
Yeah. All right. Well, okay. I don't think it. So FiddlerBot's he's got the ROS operating system on it, and then he has a pan tilt camera. He can see objects. He can find objects and grab them with his claw. I'm not showing that tonight because I showed that on the last meeting. This time I've updated him with a really nice motor controller, which is a normal one. It's called a RoboClaw. So he can move around with a reasonable amount of precision. And my main operating node in the middle, he talks to base control with commands like, oh, I want you to go this far at this particular speed. That occurs, and a completion status is fed back while that's happening. And then you can tell him rotate this number of radians at this rate, etc. This node takes care of that. Then the PID loop and all that other sort of stuff, I'll have this out later. The PID loop and all that other kind of stuff is done in the RoboClaw, which I find is a wonderful little product. No, I don't own stock. And so now I'm going to tell him to do a bunch of things. He's got a system where I send to him via ROS a large group of commands in a file, a YAML file it's called. And each command is something like move forward this amount at this speed, or turn right, or do your camera movement, or the arm, or the laser. And so we're going to do that now. I'm not sure if the laser will go under. I think it'll maybe hit there. So we'll try this. I'm going to send the commands to him now, and he's going to, with a little bit of luck, wander around. If he doesn't wander around, I brought the video of him doing it. So he turns towards you. He moves a certain number of centimeters, and I think I got it at 20 centimeters. And now he's going to do a few things like his claw and so forth. And he's going to turn again 90 degrees and move over that way for a while, doing his claw thing again.
Are you demonstrating voice command?
Yeah, no, there's no voice command on this. That's Joe. And now we turn. Now he's going to do his laser light show. Hey, it made it. It made it. That's good. We'll be able to see it. Very exciting. Please hold the applause until. Yeah. So he's got a laser, and he can see with this cam. He also has a web interface, and no, he's not going to go off. I trust him. I did this about 6 times at home today. So that's the fast mode, or medium speed. That's backwards, showing he can go collinear back and forth. This is his web interface. We're not showing this today, but this has got JavaScript and all kinds of cool stuff. You can control him here. All the commands and status and what he's doing shows up. This is a picture of, I can make him go and find objects. He'll turn towards them, turn on his laser and give it a shot, and then turn around and do all kinds of fun stuff like that. So that's FiddlerBot, and he's all done for today. Hope you enjoyed the show.
One question.
Is he running code entirely internal, or is he getting any instructions from an external?
Yeah, so all I'm doing here is okay, so he's got a Wi-Fi access point, and so I talk to the Wi-Fi access point, and I connect to him with ROS screens, just normal, boring text screens. But I could have done it with this, but I didn't want to get the thing all slowed down. And then I send him a bunch of YAML, which is a command for each thing. Go forward 10 centimeters and then turn right and so forth. He does all of that. So I hit enter. After that, he had the entire plan, and he was doing it all himself.
Excellent. Very nice.
It's not a robot, but it's a fun project which I'm doing using ROS. So this is Adafruit's NeoPixel tile, and this is connected to Arduino, and I'm using ROS Arduino bridge, ROS serial. So this actually I got it from Greg Maxwell 4 days ago. It's hardware, whole hardware, and they want to eventually use this thing on their robot for diagnostic purpose, so it can send message publish the message and put it on this NeoPixel. So I'm just creating an interface here right now. So here what I'm doing is publishing a message which will go through the ROS serial. And print it on this NeoPixel. Okay, I got it working. One sec.
Is the battery on?
No, I know what's wrong. It's ROS serial wasn't running, so the bridge wasn't running. Okay, hopefully.
Hey. Can you lower it so we can see the camera?
Just lower, there.
There we go.
Okay.
That's it.
Do it one more time.
Yeah.
So this is all through ROS serial. And there's one message my daughter wanted me to print. So I'm just going to put that.
Oh, do your homework. Clean it. Just a little lower.
Lower.
Robots are fun. She wanted me to print.
We agree.
The amazing power of ROS, Robot Operating System, can run your $100,000 computer and it can blink an LED. But it's an amazing amount of power that was taken just to turn on that display. So for those of you who haven't used ROS before, that's actually quite an accomplishment what she did.
This is so this is our a video for our prototype. This is partially aspirational and also partially real. The guts actually exist. The outer covering and the whole thing doesn't really yet. We're working on that. And we're also trying to raise funding, which is also kind of why I've been stressed a lot lately, because I've been going through that whole thing. So here we go. So this is our restaurant robot for serving and bussing tables. Like I said, the guts actually exist. They're in a locker at Tech Shop up in San Francisco. We bought like about 50 service trays and a tablet, and that's actually a SolidWorks model from the guy who's our mechanical engineer that we roped into this. And we've been slipping some pizza under the door while he's been slaving away on this, and I've been slaving away on getting fidgets and motor controllers and various other ROS nodes working. So that's kind of what I've been working on recently. The idea is it has multiple trays inside with meals on them, and you have a little roller door here that comes up and closes, and it pulls up a tray, and then it maneuvers over to your table and pulls down the door and puts the tray down on the table in front of you. And then you take it off and you pat it on the neck and it says, "Nice robot." Then it will come. Then there's currently we're kind of pitching this both as service and busing. I'm arguing more for busing because I think that'll be easier. So everybody agrees with me, but we'll see where this goes. So yeah, that's pretty much what I've been working on. One thing, and then to go along with it, we have where is here we go.
Gee, that looks familiar.
Yeah. This is the RoboPeak lidar. I actually this was my Teach Myself Onshape project. So I modeled this in Onshape. And then I don't have time to show it right now, but I actually transferred this over to Gazebo. My laptop over there that I don't have time to show. I have this as a Gazebo node that's actually using the laser array sensor, and it actually works in Gazebo. So there's that. And then one final thing, I'm going to go over here and pitch my Ansible script called Laniakia, which is a series. I think I mentioned this at SVROS, but I don't think I've talked about it here. This is a bunch of Ansible scripts that basically install ROS and the Ubiquity image and everything onto your SD card so that you don't have to keep going through the directions step by step over and over again and again every time you want to flash a new SD card or every time you want to install ROS on a new machine. So there's a bunch of Ansible play scripts or playbooks here that you just basically stick an SD card in your laptop and it just goes off and it does it. And then afterwards, you plug the SD card in your Raspberry Pi or BeagleBone, connect it up over the network, and there's another one that goes and contacts it over the network and pushes a whole bunch of other useful ROS packages onto it, sets up wireless networking, sets up a bunch of other stuff, and then by the time that you're done with all of that, you are basically ready to go. You have a fully functional ROS-capable robot running the Ubiquity distribution. There are switches where, as part of the post-install, you can either continue down the Ubiquity platform, down the Ubiquity tree, or you can move to Camp's BV80 botvac platform and install the packages for that as well. I'm taking
the Neo botvac 80.
The Neo botvac 80, yeah. I'm taking pull requests and patches because I would like more people to use this. I would like this to become kind of the standard way that we make, at least in the club, we make ROS robots, because I don't know about you, but I'm tired of looking up the web page and following the... So, and if you have packages you would like to see in this, please send me a pull request or a patch or something, and I'll put it in there.
Steve, you've got a link to Ubiquity's download page, but I don't get it. Do you install Ansible and then where do you go? What do you do?
Yeah, you install Ansible. You install Ansible on Fabric. These are our Linux tools.
Got it.
Okay, so
you can post this. If
I'll post it to the list, and it's on. This is the README for my on my GitHub. So it's called Laniakia, which is a turtle birthing ground in Hawaii. On the Big Island.
That's what you use to make the micro SD card for the Raspberry Pi that goes in the botvac.
Yeah, and you can either flash a botvac after you do the initial step. You can either do a botvac, or you can do
Steve
the
made
Ubiquity.
it easier, right?
Yes. So this is supposed to be like pretty much one touch, ROS out of a box kind of type stuff. That's
no, you
the
gotta
goal.
suffer if you want to see dude.
Suffering's overrated, man.
Suffering is overrated. I've done it before. It's overrated. So there's a bunch of different playbooks, and just
very nice.
That's it.
There you go.
Technology.
Sorry, technology in action. So I didn't know, Cam sent out the email at some point that this was supposed to be in RoboGames recap kind of setup. So that's what I tried to do here. So yeah, Cap mentioned it. I was more successful this year than last year.
Yay.
Third place with the
Silver and bronze.
tabletop and one. By the way, please come to the RoboMachine competition. Not only sign up, show up. there were a couple of people.
And compete.
Yes.
Very nice.
There were a couple of people who did not really pull through. So, tabletop, it's relatively easy to start, and actually for this one I got some more information online. And yeah, my idea here was to push Lego basically how far it would go. It's a combination of Raspberry Pi without ROS in this case, and Lego pieces, and an Arduino to handle all the sensor data.
Marco, can you briefly just say what your bot did on the tabletop?
The bot did all the basically levels. So first off, move on the table from one end to the other and back.
Same thing that camp does.
Yeah.
Tabletop, yeah, navigation is.
I wasn't sure if they did
tabletop
different over
challenge.
there.
No, that's basically the same.
We have our own
as-
Olympic event. Seriously.
Yeah. So nothing new there. If you have a table board here, you can easily bring it there and run it there. But yes, more participation would be good. So it has a little screen to show what it actually sees. I usually try to create some feedback so that I know what the robot is thinking about. And okay, that's the rain setup for Entdecker. So a big Turkey oven bag made a very nice rain cover. And I actually thought about what to do if it ever rained when I started this, and it worked out pretty much okay. So that's the infamous first cone run.
And that is some thick grass.
Yeah,
Can you turn up the volume? Put your microphone up to the speaker. It's real cute. Let's go for bonus cone 3, the one in the tall grass. The toughest bonus cone out there. This is a 0.1 multiplier. It effectively decreases your time by 9%.
and yeah, I was really stuck. So it thought its way out there, but it was basically stuck there for.
No, you make it both times. Am I giving something away?
So it's, yeah, tall grass and wet tall grass is really bad for those tires. So they are stuck.
That's great.
So what's the problem here?
The problem was that
Oh, he's in a
it was
rush.
supposed to basically back up, but it didn't move the same way as it had almost before with the grass. And
Grass
Oh,
1,
yeah,
grass
that's
0.
nasty.
yeah, pretty much.
This is like 234 feet from the goal. That's your score. What were you thinking, Marco?
Yeah.
Well,
Did
if
you
the
get the
grass
second
was,
and the third right?
I have a video of the dirt run as well.
Do you have it queued up or you're holding
Yeah.
that?
Thanks to Mark. I don't know if I ever met him.
That one's classic.
Yeah. So that's actually an overview of what's inside of the robot. There's, yeah, just to give you a bigger picture of it. So there's basically what I would call the drive system. I decided on the RC chassis just because it's easy and you get a water resistant setup pretty much for free, or for money, but you don't have to worry about it anymore after that.
So what are you using for your main processor?
The main processor is actually an Odroid U3.
So what?
Odroid U3. So I have a Deadman switch which actually tries to actively brake and steer straight. So no matter what the autopilot or U3 does, it's trying to do the right thing. That's somewhat hard to read. So there's a full autopilot on it, which has open source software and is also used basically in copters and planes and now in boats and rovers. So this little guy does not know anything about drones. But everything what it does is basically sent to the ground control station and to the U3 so that they can make more decisions about it. And that's actually the main processor setup. So there's the 3-core U3 4-core ARM processor. It's now 2 years old and it's still more powerful than the Pi 2. So, yeah, what does it do? It does the camera and through the little Arduino shield it does the touch sensors. And yeah, this year I added some status displays simply because last year I simply didn't know what the robot was doing. That helped somewhat.
When you say it takes over when the phone was discovered, does that mean there's two separate paths for figuring out which direction to go?
Yes. So there's basically the autopilot, which has a set of GPS waypoints. At certain points, I turn the camera on, and basically there was OpenCV stack tries to locate a cone in the image. And when it finds a cone, it sets the autopilot into manual mode, and then basically sends RC commands to the autopilot, which it then forwards it to the drivetrain. So that is the idea with the second GPS, why I didn't connect it directly to the autopilot. I tried to use differential GPS with my own little base station on the car, basically 300, 400 yards away.
So when Indexter was going to the orange Cone Bones 3, can you tell when it switches from GPS to camera? Is there any outside illumination or something? Or?
You see when the camera switches on, and
Okay. You actually see the camera switch on?
Yes.
Okay.
Basically the camera.
So then it's gotten to the GPS location?
Yeah, and the sound changes. There are actually two different sirens, and the second one is basically when it's
Different audio
searching.
tone? Okay.
When it's searching for the code.
Fascinating.
Yeah, that was my first idea of getting some feedback.
Okay.
So yes, the audio is not only to
No robot thinking.
entertain the people around, but actually it has
Well, it's a safety
more
precaution.
purposes. So I'm not actually sure how well it worked. At home it worked perfectly, but with all the clouds and the rain, and I'm not so sure. So that was actually my mission plan for all drones and going to the
Wow.
goal. Up to this point I made it. in the first and second run.
So where's the start code? Is that it over there?
That's the start.
That's over there, okay.
Yeah. So that's the rest of walking to the start. And here we have an GPS glitch, basically, which moved this position all the way down here for a brief moment. Yeah, and then.
Cool. Building C.
Yes.
You found that.
Okay. So the autopilot knows nothing about phones, but at certain points I turn on the camera based on the waypoint, target, altitude, because it's simply not used usually in the rover. So when the target altitude is over 1,000 meters, then I turn on the camera and the UTP tries to find the cone. When it finds it, it basically moves the autopilot to manual and sends RC commands. If nothing is found, then simply the autopilot goes on to the next waypoint and as nothing would have happened. And that's why I can basically drive the complete course without any problems and hit whatever cones I find now.
Let's see.
So, what went wrong? Yeah, on Friday I did some test runs and I realized that the approach speed on blacktop was really fast, and on the tall grass it really didn't move. So I tried to make that a little bit more dynamic based on the speed I was actually traveling, but that did not work as well as I had hoped. It will hopefully be fixed by the next competition. So, what's next? Okay. If you want to look at the robot afterwards, it's getting crowded. And so I'm thinking we have to find a lot of money for the next one. Yeah, I have very little changes in the actual RC base up to now, or up to Hobo Games I had nothing. Right now I have basically a wheel encoder in there. And yeah, I will try that and see how well that works. So the Tegra would be an option, but it's much larger than what I have on there right now, and it doesn't bring the. Right now I need 6 USB ports, and that's a little bit too much. Okay, so that's.
Is this your final run?
Yeah, that's the final run. Close to the
Those 2 runs, you went for the bonus cone 3 and basically stopped there, right?
Yes. And here I basically deleted some waypoints.
Straight to the goal cone.
Yeah.
What you should have done the first time. Get out of the way.
Yeah, that's actually my son. And since I had this GPS glitch in the first run, where the autopilot decided, okay. Yes, it's supposed to hit the cone and stop there.
Need a wider beam.
Yeah, and that was basically the problem with the speed. Okay.
Walnut green.
Yeah. Mark, what?
Play the video one more time. At least the last part.
Yeah.
Let's see if that works. Oh, doesn't work though.
Send a link on the mail list.
Yeah, it's actually in your pictures page. That's where I found it.
I'll have to take a look at that.
Yeah,
I'll post it.
They are on there.
Give us the
Okay.
frame to repeat over. Yeah. That's a classic run though.
Okay, that's it for me. Thank you.
Congratulations on your 2 L's.
So this is a message presentation. The message is that speech is easy. And so I'll show you what I did and comment a little bit about it. I started out to do speech commands for the Ubiquity robots. And the first thing I looked at was a couple of programs called Jasper and Sphinx, which comes from Carnegie Mellon. And both of those are programs that could run in a Raspberry Pi on a robot. And then, I don't know how it happened, but I found out about something called the Web Speech API, which is part of HTML5. And I either realized or convinced myself that the robot isn't the place for speech recognition. Rather, the controlling system is the place, because the robot could be far away. And you can't make yourself understood if it's in another part of a large room or a building. And also, you are subject to a lot of interference from noise and other talk and so on. So I adopted the strategy of using the Web Speech API, which runs in the browser. And here's what it looks like. There we go. Welcome to this demo of controlling a robot with speech commands. The speech recognition occurs in the browser, so the first thing to do is to connect the browser with the robot.
Connected.
Then we can enable the microphone and begin to issue commands. Forward. Go back. Forward 4 meters. This is running on Stage, which is a ROS simulator.
So is this voice recognition, is this a ROS node or what?
No, the voice recognition is happening in the browser in this web page that you see on the left.
Address how you said go forward and then it navigated around that U-turn. That seems to be more than just forward.
Hang on, because when I'm done, I'll come back around.
Oh.
Waypoint kitchen. Rotate left 20 degrees. Rotate left 20 degrees. Forward 3 meters. Forward 2 meters. Waypoint garage. Waypoint garage. List waypoints.
The waypoints are garage, office, kitchen.
Go to office. Thanks for watching this little demo. Okay, so the thing to realize is that I haven't done a thing. All of this robot motion that you saw is pure ROS. All I'm doing is sending commands, sometimes move base, and sometimes other commands. And let's run through it again, and I'll stop it and make some comments as we go. So let's see if I can do that. Welcome to this demo of controlling a robot with speech commands. The speech recognition occurs in the browser, so the first thing to do is to connect the browser with the robot.
Connected.
Then we can enable the microphone and begin to issue commands. Okay, so when I clicked the connect button, it connected to the address that was in that little address box, and that used ROS Bridge, which is a component of ROS, and well, ROS Bridge is the component that runs in the robot, and there's a JavaScript module or library that allows you to make that connection. So this just sent a message to the robot, and the robot ROS Bridge acknowledged the message, and so the browser, the web page that I wrote said connected. Forward. Go back. Now, let's see. Okay, you can see at the bottom of the page is an echo of the command that I gave, and sometimes you'll see it in red because it's a command that isn't recognized. So what the web speech API does is listens for the phrase that's spoken and gives you 10 alternative interpretations of that phrase. And so the program just goes through those interpretations and says, are any of those commands? And tells you which is the first one it hit that is a command, and it interprets that and uses it. Forward 4 meters. Okay, so up to now, the go forward and go back are just geometry commands. But this is a command to move base, saying go forward 4 meters in the coordinate system that's based where the robot is. And all this works beautifully because it's simulating, and we don't have to worry about slipping wheels or anything like that, right? So it's executing forward 4 meters, and the spot that's 4 meters ahead is blocked by the map. And so it has to go around and find the place.
What do the colors represent?
Waypoint compass. To be honest, I don't know. Those are part of the way Ross and Stage interact. They indicate the robot's computations of its cost map and its obstacles, and more than that I can't tell you. Because I really just built the control side of this thing. Okay. Back 4 meters. Okay, and now it's got to retrace its steps. And you notice the back 4 meters command is reflected on the bottom of the web page.
How does your web page talk to the robot?
Waypoint kitchen. Okay, so that's Ross Bridge. 20 degrees. Sorry, I didn't get it stopped. The answer to that question is that's the function of Ross Bridge. So there's a the program for the web page is HTML and JavaScript. And there's a JavaScript library that allows you to that communicates with Ross, which is running in the robot. So we'll go back. Oh, yeah. Waypoint kitchen. So I set a waypoint and noticed that there was a little box that popped up and said confirm the waypoint. And that's because the names of the waypoints aren't commands, and so the program has no way of knowing that it heard it right. So it asks you, did I hear this right? Waypoint kitchen. There's that confirmation. Rotate left 20 degrees. Now I didn't say that fast enough, and so the command wasn't recognized until you see it in red at the bottom of the web page. And I have to repeat the command now. Rotate left 20 degrees. Forward 3 meters. Forward 2 meters.
So web speech is always listening. You talk, and it notifies you and sends you a list of 10 things it thinks it just heard, and then you act on those based on whether they match commands you feel you should recognize.
That's exactly right.
Okay, thanks.
So is this web speech API, you're using Mozilla, right? Is it a function of the web, or is it an actual website you go to?
No, this is a, okay, I didn't cover that. The web speech API is part of the HTML5 specification. Not everybody has implemented it. Google Chrome has implemented it. Opera has implemented it. And it is said, and I haven't checked it, that Firefox has implemented it, but under a configuration. Safari has not implemented it. In fact, Chrome running on Apple hasn't implemented it. So what can you do this with? The answer is you can do it with, what I've done it with is Chrome on Windows, Chrome on Android, Chrome on Linux. Okay, and when I say Chrome on Android, I also include on an Android phone.
Wow.
And I wrote the web page using a thing called Bootstrap, which comes from, what are those guys? Twitter. Okay, and Bootstrap has the ability to not exactly scale, but adjust the image of a web page to fit the size of the screen that it's looking at. Okay.
So does it ship the speech off to a server to be translated?
It can, it usually does, but it is, but on an Android, Google can download the speech recognition, and so you don't need to use, you don't need to have an internet connection in that case. And I have tried it, but I haven't done it much, and so I can't really tell you how well it works.
Will you get to specify the dictionary of words it recognizes?
I don't know the answer. I mean, all I know, all I downloaded was the English dictionary. I don't know what it would have done if I had said German. Tried to get it to do that. Waypoint garage. So it sets another waypoint. List waypoints.
The waypoints are garage, office, kitchen.
That's a little tricky because if you don't shut off the speech recognition when you speak out an answer, it'll listen to itself and misinterpret the command. So the only real to-do left in this that I know of right now is making the waypoints persistent. They're not persistent, and that's because in ROS, parameters are not persistent. And we use ROS parameters for waypoints. But I'm planning to do that. Thanks for watching this little demo. And let me mention a couple places. Okay, all this stuff is on GitHub, and you can see where it is. It's Ubiquity Robotics speech commands. And there's nothing in it, there's nothing in this program that is bound to Ubiquity Robotics. This is all ROS. I mean, this is all interfaces with ROS. So you're welcome to use it. And one or two other. I referred to ROS Bridge. This is the ROS page for ROS Bridge. Describes it quite well. This is the page that describes the Web Speech API, and it has both speech recognition and text-to-speech. And finally, there's a nice web page called Can I Use? And this, you can look up any HTML or CSS function, and it tells you which browsers have implemented it and which versions and so on. So that's a handy reference. Okay. Any questions? Good, thanks.